Hello friends, I welcome all of you in TYBSc mathematics class. In this academic year, I will teach you mathematics paper 2 real analysis 2. Our syllabus is designed from books Methods of Real Analysis by R.R. Goldberg. Then a first course in mathematical analysis by Somsundaram and Chaudhary. So we'll cover the topics Riemann integral and sequence and series of functions from Goldberg book, while improper integral through mathematical analysis by Somsundaram and Chaudhary. So today we'll start our first topic, Riemann integral. So you are well familiar with indefinite integral, definite integral, which are studied at higher school level, that is in 11th and 12th standard. So what you have studied, if dy by dx of fx is equal to gx, then integral of gx dx is equal to fx plus c. Fx plus c. Is it right? And integral of a to b gx dx is equal to fx from a to b, which is equal to fb minus fa. You are well familiar with this. Now in Riemann integral, we will study the concept of integral for bounded value function and which is continuous almost everywhere on AB. So for that, we will now define, as I said, that Riemann integral of bounded function and continuous almost everywhere function exist. Therefore, we must know what is meant by continuous almost everywhere. And for that, we require the concept of set of measure 0. Set of measure 0. So, first we will define set of or length of interval. Length of interval. If j is equal to, it may be open interval AB, close interval AB, or open close interval AB, or close open interval AB, then length of j is mod j is equal to b minus a, and which that this length is also known as measure of j. Measure of j. Okay. So measure of interval is defined in this way. Now by using measure of interval, will define set of measure 0. Set of measure 0. So a subset E of R1, what is R1? Set of real numbers, is said to be set of measure 0, is said to be set of measure 0 if for given epsilon greater than 0, for given epsilon greater than 0, epsilon may be very small, there exist finite or countable number of open intervals, finite or countable number of open intervals ij's such that E is contained in union of ions over n and summation of length of in over n, this must be less than epsilon. This must be less than epsilon. Roughly speaking, if subset E of R1 is covered by finite or countable number of open intervals, is covered by union of finite or countable number of open intervals such that sum of the lengths of intervals, all intervals must be less than epsilon, and which is true for any epsilon greater than 0 even though epsilon is too small. Is it right? So for example, for x belongs to R1, singleton x is contained in x minus epsilon by 4 for x belongs to R1 and any epsilon greater than 0, singleton x is contained in x minus epsilon by 4 to x plus epsilon by 4 is equal to j or I where length of I, what will become this? X plus epsilon by 4 minus x minus epsilon by 4, which is nothing but 2 epsilon by 4, which is epsilon by 2 is less than epsilon. This implies singleton set, singleton x, okay, is of measure 0 for any x belongs to R1, for any x belongs to R1. Is it clear? So thus every singleton subset of R1 is of measure 0. Okay, that is measure of singleton x is 0 for any x belongs to R1. So this is the symbol. Okay, so note, if is of measure 0, then measure E is equal to 0. We will denote it by this symbol. So this is about the set of measure 0. Now we can extend this for finite set, then countable set. Means we are going to prove that every finite subset of R1 is also of measure 0. Then countable subset of R1 is also of measure 0. So next example. So let E is equal to say x1, x2, xn be finite subset of R1, be finite subset of R1 containing n points. Then is contained in union of xi minus epsilon upon, I'll take how many points are there? n, so I'll take here 2n to xi plus epsilon upon 2n, n equal to I equal to 1 to n, where summation of which is equal to union of ij or I equal to 1 to n, where summation of I equal to 1 to n, length of I is equal to. What is this sum now? Well, this is less equal. Some interval may be overlapping each other. So, what is length of each interval? Xi plus epsilon upon 2n plus minus xi minus epsilon upon 2n. So, we will get it is 2 epsilon upon 2n. So, what we will do here, instead of that we will take 4n, okay. So, we will get 4n here. Is it clear? So, which is nothing but this 2 get cancelled, 2 get cancelled. So, summation of epsilon by n, how epsilon upon 2n, epsilon upon 2n, how many times? N times. So, which is equal to epsilon must be less than, which is equal to epsilon by 2 is less than epsilon, is less than epsilon, okay, where epsilon greater than 0 is, where epsilon greater than 0 is arbitrary. There is no any restriction for that. So, it contains an infinite number of open intervals such that sum of the lengths of all intervals must be less than epsilon, whatever your choice of epsilon may be. Okay. This implies measure of E is 0. Measure of E is 0. Now we'll prove that every countable set is of measure 0. Okay. Next example. Any countable subset of R1, any countable subset of R1 is of measure 0. So that E be countable subset of R1. E be countable subset of R1. As E is countable subset of R1, so it is equivalent to set of natural numbers. A subset which is equivalent to set of natural number is known as countable set. So I can assign elements, natural numbers to members of E. 1 to first element of E, that will denote it by x1, second by x2 and so on. Okay. Therefore, E is equal to x1, x2, x3 and so on, as E is equivalent to natural number set. Now, for epsilon greater than 0, for epsilon greater than 0, now it's which is equal to union of singleton xi, I equal to 1 to n. Okay. Now each singleton xi is of measure 0, measure 0. Therefore, for given epsilon greater than 0, for given epsilon greater than 0, xi is contained in singleton xi is contained in xi minus epsilon upon 2 raised to n plus 1 to xi plus say I plus 1 to xi plus epsilon upon 2 raised to I plus 1 is equal to II, where length of II, this will become 2 times epsilon upon 2 raised to I plus 1, which is epsilon upon 2 raised to I for every I. Then E is contained in union of I equal to 1 to infinity, where summation of length of I equal to 1 to infinity, this is less equal. Now what is the length of I1? Epsilon by 2 plus epsilon by 2 square plus epsilon by 2 cube plus dot dot etc. So this is your geometric series. So its sum is nothing but epsilon by 2 is taken to be outside. So we will get 1 plus epsilon by 2 plus 1 half plus 1 half square and plus dot dot etc. Is it clear? And then this is nothing but it is geometric series. We know that 1 plus r square plus dot dot etc. is 1 upon 1 minus r if mod r less than 1. So this will become epsilon by 2 into 1 upon 1 minus epsilon by 2. Is it clear? Half, which is equal to epsilon. So here length of II is epsilon upon 2 raised to I. So I will get less equal. Okay. So from this, E is of measure 0. That is, every countable set is of measure 0. Every countable set is of measure 0. Is it clear? Therefore, note set of natural numbers, all natural numbers, or n, z, q are countable subsets. Or A is equal to 1 upon 2 raised to n where is in n. Okay, B is equal to say root 2, 2 root 2, 3 root 3 and so on are countable subsets of R1, and hence of measure 0. Right. In fact, we have theorem that if E1, E2, E3 and so on are countable subsets, or countable set are sets of major zeros, sets of major zero, then union of En is of major zero. Is of major zero. Very important result. So by using this also, I can prove that every countable set is of major zero. Again on same line, we will prove this result. Proof is parallel to what we have done for every countable set is of major zero. Okay. Proof. Here each n is of major zero, is of major zero, and therefore for given epsilon greater than 0, each contained ring is covered by En is covered by finite or countable number of open intervals, countable number of open intervals, say INJs, j is equal to 1 to dot etc., such that summation of length of INJ over j, this must be less than epsilon upon, I'll take here 2 raised to n plus 1. Two raised to n plus 1. Okay. Then E is equal to union of En is contained in union of INJ over j and n, where summation of INJs j n, this is less equal summation of epsilon upon 2 raised to n plus 1, n equal to 1 to infinity, and then if I take epsilon by 2 outside here again, which is equal to epsilon by 2, okay, epsilon by 2 square, 1 plus half square and plus dot etc. So its sum is epsilon upon 4 into 1 upon 1 minus half, sum of geometric series, which is equal to epsilon by 2 less than epsilon, which implies measure of E is 0. So from this, E is of measure 0, that is countable union of set of measure 0 is of measure 0. Okay. From this, E is equal to union of En over n is of measure 0, is of measure 0. So by using this result also, I can say that every countable set is of measure 0. Is it clear? Because this theorem actually states that countable union of sets of measure 0 is again of measure 0. Is it clear? So this is just if then condition, not if and only if. Means there exist uncountable subsets which are again of measure 0. So we'll study that in next lecture. Thanks for listening lecture carefully. So for writing the note from board, what you have to do, if I am writing, if I completed this part here and if I am explaining this part here, then you have to stop that video and you have to complete this side. Then if I come to on this side, then you have to complete this part by stopping video. In this way you can prepare your notes on your own. Thanks for listening lecture carefully. Bye bye.